as I said, of the set 5. We have done this. Yeah, until now I didn't put it in Moodle. Yeah, as I said, I was sick around 1 week, but I will do it today with this what we are doing now, and also the lecture, and I will put the solution of it in PDF file. Okay. Now going to the second exercise, we have the point mass M here, which is attached to the rod here with length L, and which is supported here in point A by PO, yeah, without frictions. Okay, then it means here if there is forces, let's say, on this pivot or hinge or support, in this case that we have only two, let's say, forces, one in vertical and another horizontal force. That we say now at time t equal to 0, okay, the initial state, yeah, the system is released from the position phi0 is equal to pi divided by 6. That means at 30 degree, yeah, and the motion occur and the influence of gravity. Now it is asking to use Newton and the D'Alembert, let's say, methods, yeah, to determine the rod forces S as function of the angle phi. That it means, yeah, we have to do free diagram. That it means to cut here, yeah, and to look to the rod forces. Rod forces is always along the direction of the rod, yeah. The extreme value of this rod force, the angle phi1 at which the sign of the rod force changes, and the rod force at phi equal to 90 degree. Yeah. Now, if I go to the solution, yeah, we will choose first D'Alembert, Newton, and after this D'Alembert. If we do so, I return back now to describe the forces which can happen here. Now, for the Newton law, if we use Newton law, what we have here, at this position, the initial position, phi0, and with, let's say, motion or solicitations, yeah, then at any arbitrary position or an arbitrary time or arbitrary angle phi, we look what it happens. That it means we look which forces are acting on the mass m. If we isolate now the mass m, that it means we do the, let's say, the free diagram, yeah, that it means we cut the rod, okay, and we isolate the mass, and we look which forces are acting on it. As we said that it's only the motion occurs under the influence of the gravity. That it means we have the weight now, mg, yeah, and we choose the following coordinate system, okay? Instead to use the coordinate system x, y, we use this coordinate system. It's free, yeah, to put it somewhere here where you have a, for example, an and you have at, yeah, it's up to you. We took it, for example, here on the mass, yeah, and we have here the axis an, which is along the direction of the rod, and we have the tangential one, yeah, where the velocity, yeah, is described that it's the same, the velocity is the same direction as the tangential, in the tangential direction. In this case, we have here ET, which is perpendicular to EN. This is the unit vector or the basis vector, and we have seen this. Yeah, we have a different way, yeah, to represent the motion, either to use the polar coordinate system, Cartesian coordinate system, or this system when we know, yeah, following the path of the motion. Now we have EN, ET. Okay, this is the basis vector, as I said, and we have these forces. Now it's only with Newton law we do the equilibrium condition. Okay, now if we do so, yeah, what we have, here, we know that the sum of the forces is equal to the mass multiplied by the acceleration. This is the Newton law. Yeah. Um, one moment. Okay, I open one file. It seems it's not here. I have to close it and to open it again. Okay, then we said that we have for the Newton law, yeah, which is known that we have the sum of the forces, different forces in n direction, it's equal to the mass multiplied by a, the acceleration in n direction. And we have the same, the sum of the forces in tangential direction is the mass multiplied by a tangential. Okay, this is the two equation that we can, let's say, the two equilibrium um, equation in dynamics, yeah, where we can describe now the relationship between, let's say, the forces due to the acceleration and the forces, the external forces. Now, if we look what we have as forces, if we take here the sum from this is, I call it A, yeah, and this is the equation B. If I take A, what we have S plus M here, G, the weight of the mass multiplied by cosine phi. Okay, this is equal to the mass multiplied by the acceleration, or let's say the, the magnitude of the acceleration in normal direction, an. Yeah, we know that from the previous, let's say, set for the description of the normal for the particle of the normal acceleration and the tangential acceleration. You look to the lecture, if you remember, it was always an, it's omega cross the vector position r. In our case here, r, it's only the length of the rod. Yeah. The second now, omega, it's only phi. If we do it's this in omega, sorry, it's only phi dot. Then in this case here, I will write it in red, an, okay, it's only L phi dot square. Now, if we look to the equation B, okay, what we have in equation B, if we look what we have the external forces only here, mg cosine sine phi, and this is equal to m acceleration in tangential direction. Now the acceleration in tangential direction, at, the same principle. If you look to the lecture or some exercises, yeah, for circular motion or circumferential motion, in this case we have at, it's only omega dot cross r, yeah, and omega dot in our case is only phi dot r, as I said before, it's only the length of the rod. Then we have here L phi dot L phi dot. This is the expression for at. Okay, then it means if we look to the equation now, what we have, we will get the following two equations. Okay, that S plus mg cosine phi equal to m l phi dot square. And we have the second equation, which is m g sine phi. This is equal to m l phi dot. These are the two equation. I wrote it by one, and the second equation, yeah. These are two equations now. Okay, this what we get from the Newton. Okay, what is known, what is unknown? Unknown is the rod force S. Okay, phi dot and phi dot dot. Then we have here three, let's say, unknowns. Yeah, and we have only two equations. The system cannot be solved. Yeah, we will see how, yeah, to solve such system. Now coming to the same equation, Newton law. Instead to use Newton law, we use now, let's say, D'Alembert. With D'Alembert, we have the opposite. Instead to have the sum of the forces equal to the mass multiplied by the acceleration, we have the sum of the forces, yeah, is equal to zero. Means, if I return back now to the representation of the forces, now if we look, the same principle as before, we have for D'Alembert principle, the same principle we use. We have the initial state at phi0, at phi arbitrary position, and we have the external force. If we cut, we do the free diagram, then in this case we have the external forces mg and the rod force S, yeah, which is always taken in traction, yeah, and we use the same principle. Means you use this coordinate system with unit vector an and et. Now instead of what we introduce extra now, it's what we call the inertia forces. Okay, what we have the inertia forces along tangential direction, and we have the inertia force which is along the normal direction. Okay, normal direction, then we take the force which is opposite, yeah, to this direction of the acceleration, let's say, or the motion. Then it means the motion is moving like this, okay? Then we take the force opposite to this motion. In this case, this force here is along tangential direction. Then we have here the D'Alembert or force or inertia force. It's only the mass multiplied by the tangential acceleration. The same principle we use for the normal direction, where we have the D'Alembert or inertia force. It's only the mass multiplied by the normal acceleration. Okay, now if how to describe this in equations, what we have here for the D'Alembert, okay, we have the sum of the forces the same along normal direction is equal to zero. Okay, the same here. What we have, we took here a mass and this is for Newton, but for D'Alembert we took zero. Okay, but we introduce on the left hand side the inertia force. Okay, now this is, I call it A prime, and we have the sum of the forces along tangential direction ET, and this is also equal to zero, and this is B prime. Okay, now if I take A prime, what we have as external forces, we have S, the rod force, plus the weight mg, okay, projected in normal direction, then it's cosine phi minus F, the D'Alembert force or the inertia force of H n. And this is, should be equal to zero. Okay, the same for the equation B prime. We have the mass, the weight or the mass multiplied by the acceleration, sine phi, and this is minus also the D'Alembert or inertia force in tangential direction. This is must be equal to zero. Okay, now what we have in our case, we have F, the inertia forces in tangential on the normal direction. In normal direction, the same principle. It's mass multiplied by A n. Okay, and this is it's only the mass multiplied by L phi dot square. Okay, this is what we get as the previous one. The acceleration, the normal acceleration, this is come from the kinematic relation. Yeah. Now, if we look to the force in tangential direction, F H T, okay, this is will be M multiplied by the tangential acceleration, and this is only ml phi dot dot. Okay, then we have now the two equation. Then we get here the same principle, two equations, which are here as plus mg cosine phi minus or equal to mass L phi dot dot square. And we have the second case that we have the second equation. This is mg sine phi will be equal to the mass multiplied by L phi dot dot. This is will be the equation 1. This is will be equation 1. If I can write 1. And this is the second. Now, if you look, we have now here from this one, the relation 1 from Newton, okay? Then it's the same as this one for D'Alembert. And the second equation also, it's for Newton here, is the same as D'Alembert, okay? Then you have always the choice to use either D'Alembert or Newton. Yeah, it's depends sometimes on the problem. Sometimes it's easy to use Newton, and there is some problems, other problems where it's more easy to use D'Alembert. Okay, now coming to this case, as I said, there is three unknown, which are the mass, the rod force S, the angular velocity, and the angular acceleration. There are three unknowns, and we have only two equations. Okay. Now, if I look to the equation, what we have from the second equation, we can see that there is here the mass. Okay. Then we can cancel it from the left and to the right one. Then we can get here from the second relation from 2, we can get here the expression of phi dot dot is equal to G divided by L sine phi. Okay. Now what we have, we see that there is this one is called the differential equation, where we have to solve it to get, okay, minimally, let's say, yeah, the expression of um, either the acceleration, yeah, or velocity, angular velocity of, or the angle phi, yeah. What we have here, this is what we call differential equation, yeah. Now, if we look, so that we can now, the first term and the second term, okay, let's say the left hand side term and the right hand side term, to put it that as we know, phi dot dot, it's only d phi dot divided by dt. It's time derivative of the angular velocity. Yeah, we can write here this, it's only d phi dot divided by dt, okay, and here g divided by L sine phi. Okay. Then what we know from the initial conditions, it said that we start at the position phi0, which is pi divided by 6 at 30 degree, and from the rest. This is the position t equal to 0, is the rest position. That is means phi dot, the angular velocity, is equal to 0. Okay. Then what we have to make, it's only to make the link between this velocity and the angle phi. What we do the following. This term here, we multiplied it by phi dot. Okay. Then what we get the following equation here, that we have phi dot, then it means we have here d phi dot divided by dt multiplied by phi dot equal to g divided by L phi dot sine phi. Okay, then we have only here the variation with phi dot, yeah, that when we integrate with respect to time or with respect to the variable, okay, we have to consider the case where all parameters are depending on this variable or on the time. Then it means if we look here now, we have phi dot d phi dot, okay, equal to g divided by L sine phi d phi. Okay, I make like this. That you see it's here d phi is the change of the angle. Here d phi dot is the change of the velocity. And we know that phi dot here, I write it in red color, phi dot, it's only d phi divided by dt. Okay, the angular velocity is only the time derivative of the angle phi. Yeah, now we have dt on this term. If we replace this expression here, yeah, then we have dt here. They cancel each other. Then we get only phi dot d phi dot g divided by L, yeah, d phi sine phi. Now I can integrate, okay? Then it means I can get here now the integral of phi dot d phi dot equal to g divided by L sine phi d phi and this is the integral. Okay, then it means we integrate now. What we get the following equation here. We have phi dot d phi dot is the same variable. Okay, here we have phi dot, yeah. Don't, it's hard to write the point phi dot and here phi dot also. Okay, phi dot d phi dot is the same variable. Here sine phi d phi is the same variable. G divided by L is constant, can be, yeah, put out of the integral. Then we get here phi dot the half of phi dot square equal to minus G divided by L cosine phi plus constant C. Okay, this is what we do. Either we know the bounds of the integral, yeah, or we put constant C and we take the initial condition. Okay, now for constant of C, here constant C is equal, it's unknown that here we take initial condition. What we know? We know that at time t equal to 0, what we have phi dot it's equal to 0, okay, and phi it's equal to p divided by 6. Okay, this is what we know from, yeah, uh, the announcement of the exercise. Now, if we do so, we can get here, when we put this relation here, phi dot, we put it, we replace it by 0, okay? Phi, we replace it by p divided by 6. Then we can get here c, it's only square root 3 divided by 2 multiplied by g divided by L. Okay, this is the constant, integration constant. Then if we replace, we get here now the expression of phi dot square is equal to 2g divided by L multiplied by square root 3 divided by 2 minus cosine phi. Okay, this is the expression of the angular velocity. Now, what we know, we can take this now, the angular velocity p dot square, we can replace it here in the D'Alembert equation, yeah, or in Newton equation, okay? Then we take this as equation 3, then we have 3 in 1, then we get here S will be equal to mg multiplied by square root 3 minus 3 cosine phi. This is the expression of the rod force. Okay, now we look, now we have for the first question to determine the force S, the rod force as function of the angle phi. Okay, now at each position we can determine the value of S as M and G, the mass and the gravity acceleration are constant. Yeah. Now we look for the second case. It's asked here the extreme value of the rod force. Extreme value, that is means in magnitude, yeah, the maximum value. Then to look to the maximum any parameter, it's only to make this parameter, let's say, as derivation of this parameter with respect to the variable must be equal to 0. Okay, then for the second question, let's say we call it S max, okay, or extreme, yeah. In this case, what we should have from 3 we make only ds over dt d phi should be equal to 0. Okay, then we can get here from this one, yeah. If we make this, then we get 3 mg minus 3 mg, sorry, sine phi should be equal to 0. Okay, this is the condition. Why? When we make here the derivation, this is constant, g is also constant, then it means this first term, its derivation with respect to phi is equal to 0. Then we have only the second term, the derivation of minus cosinus is sine phi. Okay, then we have here two cases, either, okay, phi 1 is equal to 0 or phi 2 is equal to p. These are the two conditions, yeah, that you get here. Sine phi is equal to 0. Then it means from this one, we get here two cases, S1, okay. For the case 0, okay, for phi it's equal to 0, doesn't exist. Why? Because we start from phi 0 equal to p divided by 6. Yeah, this is the initial state. Yeah, and after this, we look what it happens, yeah, to, let's say, until 2 pi. Okay, For S1, we take phi equal to P divided by 6 instead to get to 0. Okay? In this case, we get here with minus square root 3 divided by 2 multiplied by mg. Okay? And the second case, S2 for phi equal to P. In this case, we get mg multiplied by 3 multiplied by 3 plus square root 3. Okay, these are the two value. Yeah. Now, if we look now how it will be this change, okay, then I return back to the graphical representations. Okay, we look here to different case that where the value of the rod force change. Okay, there is the first case, what we said at P over 6, that is means S1. Okay, in this case, we have mg, we have the force S, and we have only the mass multiplied by the tangential acceleration. There is no, let's say, force due, okay, to normal acceleration. There is also at value of 60 degree. Yeah, these are the four forces can happen that we have the rod force S. Okay, and we have here the normal, let's say, for example, the lumbar force, the inertia force, MAN, the normal one, as well as the tangential one, and we have the weight. Now, if we take at 90 degree, okay, at 90 degree, there is always S along the direction of the rod. There is a tangential one, normal one, and the weight. This case corresponds to the second case, okay? Second case, that is means S2 at phi equal to P, yeah, at 180 degree. In this case, there is the normal force, and there is only here the rod force. There is the normal, let's say, inertia force, and there is the weight. Tangential one, yeah, it's zero. What you look here, from this part, the S is always inward, okay? Then it means the rod is under compression, yeah? But here, okay, you see that the rod is under traction, okay? Then it means somewhere from 30 degree initial state to 60 degree, the rod force, yeah, here is changing the sign, yeah, of the rod force change the sign. That is means certain times there will be the angle where the rod force will be equal to zero. Okay. Now, if I want here to express this, Now coming to the third questions where the here change here of sign. This means that S should be equal to 0. Okay? Initial from 30 degrees to certain times to a certain angle is positive, it's traction. And after this, it becomes a compression, that is means negative. Then we look for at which position S will be equal to 0. Then we have in this case, if we take the equation of S, okay, then we have here S minus 3 cosine phi, okay, I call it C, yeah, changing, plus square root 3 must be equal to 0. This is the expression, okay, from here, yeah, this is the expression of the rod force. We put it equal to 0, and we have this relation. Then from this one, now we get here phi C is equal to 54.74 degree. Okay, then it means from 30 degree until, yeah, this angle, the rod will be under traction. After this angle, the rod will be under compression. Okay, now coming to the fourth case at fourth questions, let's say, what we have, rod force for P equal to P divided by 2. Then what we have here, we have S will be equal to square root 3 mg. Okay, this is what it's asked for in the fourth question. Okay, it's only to replace phi by each value in this relation here, and you get the rod force for P divided by 2. Okay, now we come to the exercise 3. In this case, we have a mass M is pulled with friction over the ground. Here, there is friction between the mass and the ground. Here, we take this coordinate system X, Y. Okay, the coefficient of friction between the mass and the ground is mu. Yeah, we note it always by this notation. And the cable is pulled with constant velocity here, V0. The motion of the cable over the pulley occur here without friction. There is no friction between the cable and the pulley. Yeah. Furthermore, the system is under the influence of the gravity G. Okay. Given, let's say, the position X at time t equal to 0. It's 0. This is the initial condition. It's given the mass, the very initial velocity v0, which is constant, and mu as let's say friction coefficient or coefficient of friction. And now here we have the geometry, the distance C and A. Okay, what it asked here for here using both Newton's and D'Alembert law, yeah, determine the position xt of the mass m, the velocity x dot t as x dot as function of x, and the acceleration x dot dot as function of x of the mass m. Okay, the cable force F when you make the let's say the cut here. Okay, you can have the force F here and force F here acting on the mass, yeah, as well here on the rod. And the place at which the mass M lift off from the ground at certain position here, yeah, when you pull the cable at certain times, yeah, the mass M lift, and we are looking at which position exactly. Yeah. Now coming to the solution, what we have here, if we get, for example, for first, yeah, the here, what we have for the position xt of the mass m, yeah, here we do it geometrically. That it means here, if we use Newton and D'Alembert, it's only to determine the forces. This can happen that to determine also, and we see that it depends also the position. Now, coming to the case where to represent these forces, if we use D'Alembert as well as here Newton law. In Newton law, we have here we said the mass, yeah, multiplied by the acceleration. In D'Alembert, we have the sum of the forces is equal to zero. In our case, what we have as external force, taken as external force, we have the force on the rod F, okay? We have the normal force, which is the contact force between the mass and the ground. We have the friction force, which is against, let's say, is applied against the motion. And we have the weight mg, okay? We take this coordinate system, x dot x and y, okay? And we have to take also the velocity as well as the acceleration along this direction. Then it means if we apply this, we will get here two equations, yeah, the same as for D'Alembert. One is in x direction and the second one is in y direction. The same principle can be applied for D'Alembert. The differences, yeah, is here that we use what we called, yeah, the inertia force. Inertia force mx dot dot along x direction, which is against the motion or direction of the axis x, and the inertia forces m, let's say, call it fv, it's my dot dot, which is along the y direction, that is means opposite to the direction of the axis y. Okay, the same, we have the same external forces, yeah, the friction force, the normal force, the cable force, and the weight mg. Okay, if we express these equations now, here we have exercise 3. If we use now Newton law, we have always the sum of the forces equal to the acceleration. That it means we have here the sum of the forces Ex along x direction. This is equal to the mass multiplied by the acceleration along x direction. Okay. Then if we look here, what we have the forces F minus here, the forces F cosine angle alpha minus mu. This is the friction force multiplied by N equal to the mass multiplied by x dot dot. Okay, we have the second equation, which is the sum of the forces along y direction. This is also the mass multiplied by the acceleration along y direction. And here along y direction, what we have N minus mg cosine minus mg plus f sine alpha equal to mass multiplied by y dot dot. Okay, this is, let's say we call it the equation A, and here the equation B. Yeah. If we use now the D'Alembert, if we use now D'Alembert here, what we have the sum of the forces along x direction equal to 0. Okay. Then it means we get here for D'Alembert the same equations. Yeah. There is only the change of its, that it means we have only the FH and FV, yeah, which have to be introduced, which are the inertial forces. Then we get here minus mx dot dot minus mu n plus f cosine phi equal to 0. Sorry, not phi, alpha. Now the same principle here, the sum of the forces along y direction equal to 0. In this case, we have the vertical force minus m the vertical inertia force y dot dot plus n minus mg plus f sine alpha. This is equal to 0. Okay, this is, we can call them a prime and b prime. Okay, and you look, they are the same as here when you put mx dot dot on the left hand side. Okay, and the same here for my dot dot on the left side, then you will get the same equations. Okay, then you either you use these equations or these two equations. Yeah, then this, to summarize, this is to know which term this is only f h. Yeah, I call it h, and this term here it's f v, which are the D'Alembert inertia force in horizontal direction and in the vertical directions. Okay, now coming to express this, what we have here, from this, either A and B, or A prime, B prime, what we know only that the case that the force and the acceleration in y direction is equal to 0. Okay, this is, we know it. Why? Because it's parallel, not parallel, it's along x direction. Okay, in this case, we have to put here for the second, not from the second equations, but we know by principle that here there is only motion along x direction, yeah, when the cable is pulling the mass m, and there is only certain time where the mass lifts the ground, yeah, and the mass lifts the ground. In this case, yeah, there is acceleration along y direction and also in x direction. But we are not looking to this case. Yeah, we look what is asked for. It's only when, at which position, yeah, the mass lifts the ground. Okay, what it happens after, it's not asked for. Yeah. Now what we have, keep in mind that y dot dot is equal to 0. Okay, there is no acceleration in y direction before that the mass left the ground. Now we looked at here for how to describe this. Okay, we need here, as you see, x dot dot is unknown. Okay, n is unknown. The force F, yeah, it's also unknown, that we have already three, yeah, unknown. Yeah, here the same principle. If we use the second equation, when we put here this y dot dot is equal to 0, we have the force N and we have the force F. Okay, F is the force in the cable, N is the normal force or the contact force. There are two unknowns, one equation. Okay, we know we need the third one. Yeah, the third one is only to describe the kinematic relation. And for this case, I return back to the graphical presentation. What we know the distance c, We know the distance A, okay? This is where we put the coordinate, our coordinate system here, Y, and we have our coordinate system here along X direction, okay? Now what we have alpha 0. That it means a certain position here, X, okay? We pull the mass M, yeah? What we have initially here, this is, let's say, at the rest, okay? Now, at certain position X, okay, we have the velocity acting on the rod or on the cable. Sorry, not the rod, on the cable, yeah? Then in this case, we have C is given. At this position X, we are looking for it, okay? And we have here the rest, it's only sine C minus X, okay? Now the cable at this position, T0, let's say, has a length L, and after this, the cable here, this from the ground to the pulley, the cable length change due to velocity, okay? Until we said that is the mass here, M, yeah, um, let's say, lift the ground. Then we have two cases. We have these two triangle. The first one, okay, and we have the second one here. If we look, I'll return back to the note. Um, one moment, I don't find the note here. Then what we have here, we can express that from the first triangle, okay, then we have here C, we're using, yeah, um, Pythagoras, yeah, or um, Pythagoras theorem, let's say, for the triangle 2, then we have C minus X, okay, square plus A square equal to L minus V0 multiplied by T square, okay? Now, if either, yeah, I will send you the, let's say, the solution. There is two methods, let's say. Either we take the triangle 1 and 2, or from this one, yeah, this is the alternative. It's only to make, yeah, the time derivation to get first the velocity, x dot, yeah, as v0 is constant. And when you make the time derivative, yeah, you have to take in consideration the time here, okay? When you derive with respect to time, L is constant, A is constant, and C is constant, okay? Then from this equation here, we make the first time derivation, x dot, and after this, we make the second one, okay, to get the acceleration, what is explained here. Yeah, this is you can look, yeah, how to get this with respect to derivation, let's say. I will give you only to use this is here. From this, it's only geometrical problem, and with respect to the conditions, initial conditions, of course. This is triangle 2, yeah? Now, if I take from the triangle 1, what we have L, it's equal to square root of A square plus C square. Okay, this is from triangle 1. Yeah. Then if we look here, what we get from the first triangle here, from this one, from 2, we get C minus X. It's equal to plus minus square root of L minus V0 T square minus A square. Okay, then it means we have here, we get the expression for X, it's minus plus, I take another here, we get C minus plus square root, and you look here that it's only when we develop further, yeah, this equation here, okay, we get C square plus V0 T square minus 2 times V0 T here, one moment. And here we have square root A square plus C square. Okay, this is square root. Now we have here two position. Yeah. We have C, X can get C minus this term here, or X can get C plus this term. Okay. In this case, what we introduce the initial condition, yeah, to know which one is valid, because we have not the value of C and so on that we can replace, and after this we decide, yeah, if it's negative, then we uh, uh, let's say neglect it. If it's positive, then it means it's the right value, yeah. What we take the initial condition. Initial condition here, what we know, that X at time t equal to 0, it's equal to 0. Then it means we get here two cases. If we replace here on in this equation here, we get 0 equal to c minus square root c square. Yeah. And the second one, we have 0, which is equal to c plus square root c square. Okay, as you can see here, c minus square root of c square is 0. Then it means 0 is equal to 0. But this one, 0 is equal to 2 times c. Yeah, then it means this one, yeah, it's not logic. Then we can, yeah, neglect it. Then the right one is this one, the first one with c minus, okay, square root of this terms here. Then we get here now, let's say x, then it's this case, x t is equal to c minus square root, okay? I will not repeat saving the time and so on, yeah, c square plus and so on, yeah? Then looking now for, in the equation, it's asked for the velocity as function of x, okay? Now this is the expression of xt, yeah? But it's asked in the first question. The second question, it's asked for x dot as function of x. Now what we have only to make the time derivative, okay, of this equation here. Then we know that x dot is only dx divided by dt, okay. Then you make time derivation with respect to time. We have the time here, t, v0 is constant, c is constant, okay, a is constant. Then we have only to make the time derivative of this term. Then we will get here that this is will be equal, yeah, to minus here v0 square multiplied by t minus v0 square root a square plus c square divided by, yeah, the same term here, c square, okay, plus and so on. This is the expression of. Then what we have here, we have the time, but it's asked x dot as function of t, okay? Now, if we look to this expression here, t, we can get it from this equation from the triangle tool, yeah? Then we have here the expression t of the expression of the time t as function of x, yeah? This is what's asked for. Then in this case, we know from 2, okay, we can get that here t is equal to L minus square root of cis minus x square plus a square, okay, divided by v0. This is the expression of t, okay? Now this is, I call it the equation 1, yeah? Then we have here the equation, I call it 2, okay? Then I say 1 into will give now the expression of x dot as function of x. This is equal to square root c minus x square plus a square divided by c minus x all multiplied by v0. Okay, this is the expression of x dot. Now, if we look to the expression of that, that's what we have here. We can get now the forces, yeah, cable forces, let's say 3F. Basket 4. Now what we know? We know x dot, okay? We can get here now the expression of x dot dot, okay, as function of x. Then we have here the expression of x dot. Then we can make the time derivative x dot dot x dot dot here will be replaced either in A, okay, or B, yeah. Then we have the relationship between F and N. Then we have here I write from the equation, I call it B prime, yeah, B other B prime, okay, B or B prime, if either we use the number or. Here we get N is equal to mg minus F sine alpha. Okay, this is, I call it C. Yeah. Now what we have F from now A or A prime. We can get now F, which is equal to mass multiplied by acceleration, x dot dot cosine alpha plus mu sine alpha plus mu multiplied by mg divided by cosine alpha cosine alpha plus mu sine alpha. This is the expression now for F. Then we can get here for this expression now let mg here Sine alpha, cosine alpha, as alpha is, let's say, arbitrary angle, we can express it that here we can find that sine alpha from the triangle, yeah, it's only a divided by square root of c minus x square plus a square. And we have cosine alpha, it's c minus x divided by square root, the same c minus x square plus a square. Okay, then we get here the expression of f. Okay, when we are on place, and of course we have here x dot dot. As we said, we make the time derivative of this one. Okay, then we get here the expression of f. Okay, and this is, it's a long expression. Okay, you will see it on in the solution. Yeah, this is the principle. Now the question is where the point of lift of x. Then it means that here for the fourth questions, what we have to lift, that it means when the mass m lift the ground, then in this case there is no contact between the ground and the mass. In this case, n, yeah, will be equal to 0. This is the important part. Okay. Now, if we put n equal to 0, then it means here from, let's say, equation, I put it C, this one here. Okay. We put only n equal to 0. Then we get here mg minus f sine alpha will be equal to 0. Okay. Then it means we get here mg will be equal to f sine alpha, and this will be equal, if we replace sine alpha and f, then we get ma v0 square multiplied by a square c minus x cubic plus mu multiplied by g divided by c minus x plus mu multiplied by e. Okay, and from this equation, then we have here, we get x equal to c minus square root 4 for v0 square a cubic divided by g. Okay, this is what we get. And there is here only the solution which is can be valid when x max is equal to c. Yeah, if x will be max equal to c, then we get here x is equal to c plus this term here. Okay, I know it's